Okay, so right now I'm going to do a quick review of what we covered on Tuesday for those of you who are watching this class on video on YouTube. Our first class recording did not record properly, so I'm going to do this quick review for you today. We're in chapter 18 of the OpenStax College Physics textbook. And we started with static electricity and charge. Here, talked about the fact that this idea of electrical charge or static electricity was discovered a long time ago as people, rubbed materials together, either on purpose or on accident. Walking across things or whatever else, they discovered that you get a little electric shock sometimes. You can touch somebody with your hand and give them a little shock or whatever else. And the reason that they show this little piece of amber here is that amber is one of those culprits, one of those pieces of material that is easily charged up when it's rubbed against a different material. Particularly, it gets really well charged up when it's rubbed against fur or hair, so like cat fur or human hair, which is relevant because hundreds of years ago, and not even that long ago, I mean even 100 years ago, people were making things out of amber like combs for hair. And so if you're combing your hair with an amber comb, it's not that hard for you to imagine that it might get charged up with some electrical charge. The other thing that they discovered while they were making observations about these things is they discovered there are some properties of charge that are quite interesting, and that is two things that are charged up in the same manner will repel each other, but there's also this idea that some things that are charged up actually attract each other. So they started to guess that there were two kinds of charge, and that was a discovery by our friend, let's see if we can find the picture here, our friend Benjamin Franklin, which we'll get to in a minute. Of course, now we understand much more about how charge works. We understand that charge is a particle, and it's usually passed around from one thing to another in the form of the electron. And it was Benjamin Franklin that assigned this particle its name, the electron. The electron is named for electra, which is the Latin name for Latin or Greek, but it's the Latin or Greek name for amber, and that is the charge that amber collects. So amber collects electrons when it's rubbed against cat fur. But when you rub the amber against the cat also gets charged. But it's charged because it has given up electrons and it's been left with nuclei of atoms that have fewer electrons than normal. So you get a positive charge there, the electron with the negative, the nuclei with the positive charges. And we know a lot more about that now. We also have been able to discover, and we'll learn more about this discovery later, that the electron has a specific amount of charge, and that specific amount of charge is the only specific amount of charge that exists really in nature. We call that a quanta of charge, or a unit of charge, you could say, and it's we quantify it using some units that we call coulombs. The charge of an electron is negative 1.6 times 10 to the minus 19 coulombs, and the proton is positive 1.6 times 10 to the minus 19 coulombs. And that's named for a scientist who did a lot of experiments with this. But the most important thing about this is that they discovered you can't get a partial charge of an electron or a partial charge of a proton. That these charges exist in these little packages, and they come in these packages and you can't split them up. And that has a lot of important implication later on in the science of atoms and particles, which we will learn later in the semester as well. So there are lots of different experiments you can do with these things, with materials, rubbing them together and creating different charges. Another thing that we learned about quite a while ago is that in interactions, charges are conserved. They're neither created nor destroyed. And then in the 20th century, that was further proven, even in very extreme circumstances. In very high energy situations and big particle accelerators and nuclear reactions and things like this, you'll often get energy coming into a situation, and then as it kind of tries to dissipate or decay, we call it, it can actually become two particles. Energy can turn into matter in this case. And when it does, it often creates an electron, but at the same time it creates an anti-electron, which has a positive charge like a proton, but it's actually got a mass like an electron. And we call this antimatter. You get the electron, which is what we call matter, and we get an anti-electron, which is antimatter, created at the same time, so that the charge of this situation is conserved. We had zero charge before when it was just pure energy, and then we end up with an electron with a negative charge and an anti-electron with a positive charge, and when you add those together, they cancel each other out for a total charge of zero. Notice that we use Q for charge. Q total before is zero, Q total after is zero. And the same thing can happen with the electron and the anti-electron going back into energy. In situations, they can actually recombine. We call this annihilation. They annihilate each other and become pure energy. These particles essentially just disappear and become pure energy. Afterwards, the charge is zero just because the charge before was zero. So this conservation of charge is quite important, and the reason that they discovered this is because when they first observed this electron being formed, they said, wait a second, that defies the law of conservation, of charge conservation. There shouldn't be an electron just created out of nothing. And they went looking at this experiment more closely, and they discovered this anti-electron being created. And they were able to show that charge was still conserved, and they used that conservation law to discover this anti-electron. So lots of interesting stuff surrounding charge, electricity, and so on and so forth. So the next thing we wanted to talk about in this chapter is the difference between what we call conductors and insulators. And the difference is really quite simple. In conductors, which are usually metals, electrons are not bound necessarily to single atoms. Some of the electrons that are in the metal are free to move around, jump around from atom to atom to atom through the metal. And what that means is that electricity or electric charge can move around on the metal very freely, very, very easily. And so here we're showing what we call an electroscope, which is this ball of metal connected to a rod of metal going through some insulating material here that doesn't allow charge to move around. And then it's connected down here to these two gold leafs. What a gold leaf is, it's pure gold that's been hammered out to a very, very, very thin kind of paper-like substance that's much, much thinner than paper, so that it's extremely lightweight, but it's still made of metal. And there are only a couple of metals you can do this with, and gold just happens to be one of them. So it's kind of like a really, really lightweight gold foil. And if you put a charge on the top of this, that charge can spread out. So for example, if we remove some negative charges from here, remove some electrons from this, then the other electrons will spread out, but they won't be enough to counteract all the bare protons in there. And so the overall charge on this metal piece down the middle of this electroscope will be positive, and the leaves on the electroscope will then deflect away from each other because there'll be positive charge on each leaf, and the positive charges tend to repel each other. And negative charges repel each other as well, but positive and negative attract each other. But you get these leaves standing out away from each other like this. And that an electroscope is often used to show these charge effects on materials using conductors, using this conductive part of this electroscope. But part of the electroscope is made of a material that's an insulative material. It can be plastic, or it can be glass, or some other material that does not allow electrons to move around very freely on it. And those materials, you can charge them up, you can put charge on them, but once you put that charge on, it'll just kind of stay in one place. So if we charge up the side of the electroscope over here that might be made of plastic, or the face of it that's made of glass, that charge will stay right on that glass, and it won't move around to other parts, it won't spread itself out. It just stays there. And of course on the metal, the reason that charges that are put on a metal spread out is because if they're all the same kind of charge, they try to get as far away from each other as possible, because like charges repel each other. So there are different ways to charge objects. One is to charge it by contact, where you actually touch the materials together. And of course, if you touch a conductor with something that is a charged object, the charge will go to the conductor and spread out evenly, because it's free to move, the charge is free to move on the conductor. But if you charge an insulator, an insulating material, by contact, that charge will stay right where you touched it with the charged object. But you can still charge both objects. Charging by induction is something that you can really only do with conductors, because charging by induction requires that you move charges around on the material. Now here is a classic example of that people like to use in physics classes. We have two conducting spheres, and we touch them together. And when we touch them together, when they're in contact with each other, that means they're like one conductor. The electrons on one can actually move to the other very easily because they're touching. And then we bring a positively charged rod close to this left side sphere. And what happens is that attracts a bunch of electrons over to the left side of that sphere from both spheres. We get electrons coming from the right sphere and the left sphere over to this left side of this sphere attracted to that rod. We haven't touched it yet, we're just bringing it close. That means that the sphere on the right-hand side has a bunch of extra positive charges that don't have any electrons to balance out their charge. And then we separate the spheres. And when we separate the spheres, leaving that rod nearby, that right-hand sphere stays positively charged, and the left-hand sphere stays negatively charged. And then if we remove the rod, then those spheres are now charged negatively and positively, and we never even touched anything charged to either one of them. We just charge by induction, and that's one way to do it. Another way to do it is to have a single sphere, or an electroscope, or some other conductor, and bring a charged rod near it. And when you bring that charged rod near it, you get negative charges on one side, and of course you get bare positive charges left over on the other side. And then if you connect that other side to ground, which means you connect it to a pipe that's touching the ground, or drive a stake into the ground. Why the ground? Well, because the Earth is like this huge repository of electrons, and it's more than willing to give electrons to something that needs electrons, or take electrons from something that needs electrons taken away. So if something is charged with extra electrons, grounding it will take those electrons away. If something is charged with more protons than electrons, then the Earth will give it electrons to help it. Essentially what the ground does is it always tries to give an object or take a charge away from an object so that it becomes neutral. It neutralizes the charge on objects. So if we ground this object on the right side is missing electrons. So the ground will pump up a bunch of electrons to even out that side. Right? But then if we disconnect the ground and move the charge away, now it's got some extra electrons that it didn't have before. And then it ends up being negatively charged. We essentially sucked up some electrons to even out that side that was positively charged, and then disconnected everything, moved away the rod, and we have a negatively charged object now. We can also polarize things, charging by induction with polarizing. So if you're looking at the inside of a material, at the actual atoms or molecules in a material, and you bring in something very, very, positively charged very close to this object, those molecules sometimes and atoms sometimes will actually polarize. Not even sometimes, they always will, but some materials more than others. But they will polarize in a way that they will become negatively charged on one side of the atom and positively on the other, because the negative part of the atom is the electrons in the atom essentially are kind of pulled that direction, and it leaves a positive charge on the other side of the atom or molecule. Do the same thing with a negative, and it does the same thing, and the overall result is that the material has an overall feel of positive one side, negative on the other, if you have a positive or a negatively charged rod near to it here. And so it happens with lots of materials. And that explains this demonstration here of a charged rod near the water. Water is highly polarized already. Water already has a very positive side and a very negative side because of its structure. And so no matter what kind of charge you bring near water, the water molecules in the liquid will rotate very easily to oppose that charge, and then it will be attracted to whatever rod you bring near. It doesn't matter if it's a positive charge rod or a negative charge, it will be attracted to it. And that is charging by induction. Now this is where the first section that we got to concerning any equations with this section, and it's Coulomb's law. Coulomb studied the attraction and repulsion between charged objects to great degree, and what he discovered is that there is a force between charged objects that is very similar to the gravitational force in a mathematical sense. It can act over distances, and as you go further and further away, the strength of the force drops off as 1 over r squared, just like gravity. And he also discovered that it's directly related to the amount of charge on the objects, which we call Q1 and Q2, and that there is a constant involved, which we call the Coulomb constant, which turns out to be 8.988 times 10 to the 9th Newton meter squared per Coulomb squared. Of course, those units are just picked to make the equation work, but it does work. So if you want to know the force between 2 point particles, 2 point charges, Q1 and Q2, you just calculate, or you just measure the amount of charge each one of those has. Turns out to be a fairly complicated thing to do, but it can be done. Divide by the distance between them squared, and multiply by the Coulomb constant, and you will get the amount of force between those charges. And they put the absolute value sign around this because it sometimes gets confusing to figure out when you have negative charges, positive charges, so on and so forth. So we just use this equation generally to calculate the magnitude of the force, the strength of the force between two charges. And then we just figure out the direction of the force by looking at the situation. If you have two like charges, it's going to be a repulsive force. So here's what it would look like if you had two negatives or two positive charges. It would look the same. You would have a force pushing this way on the first charge, Q1, and a force pushing this way on the second charge, Q2. We call this force here the force of charge 2 on charge 1, force 2, 1. So this is the force from charge 2 on charge 1, force 2, 1. And this is force 1, 2, the force from charge 1 on charge 2. So it's the from and then 2, right? And it's a repulsive force, so we know that this one is to the left and this one is to the right. If Q2 was above Q1 up here, then the forces would be up and down on these two charges, right? And if they're, of course, at a diagonal, then it's at a diagonal. And the forces are always on a line connecting the two charges. They're always on this line connecting the two charges. Of course, if they're opposing charges, values, if one's positive, if this one's positive and this one's negative, then it's an attractive force, and you know that the arrows are going to point towards the other charge. And so it makes it just a little more complex to figure out directions, but not much. And then we do this example where they give us an electron and a proton separated by a particular distance, which is essentially the hydrogen atom. So they're asking us to calculate the force between the electron and the proton in a hydrogen atom. Well, that means Q1 and Q2 are both 1.6 because they both have, the proton and electron have the same amount of charge, just different sign. The distance squared between them is the distance they gave us, 0.530 times 10 to the minus 10 meters squared. And then you have the K constant, Coulomb constant, you plug that in. And you get a force of 8.19 times 10 to the minus 8 newtons. And you say, well, that's not that big of a force. That's actually a really tiny force. That's almost a nanonewton. It's like 10 nanonewtons. It's like 10 nanonewtons. How can that be any kind of big force? Well, remember that forces, small forces, can make a huge acceleration on very small objects. And these are very small objects. Protons and electrons are tiny. And so this is actually a pretty dang force for an electron. It would cause an electron to accelerate with 8.99 times 10 to the 22 meters per second squared. Which means if it accelerated even for a second because of that force, it would break the speed of light. Okay? So it's extreme. That's an extreme force for the electron, and for the proton, it's like 10 to the 19. It's a 10 to the 19 meters per second squared acceleration. So it's a huge acceleration for the proton as well. Compared to the gravitational force between the electron and the proton, you take the mass of the electron, the mass of the proton, and divide it by the distance squared between them, and multiply by the gravitational constant. This is from last semester. Then you get 3.61 times 10 to the minus 47 newtons. That is so much smaller than that electric force. The electric force is huge compared to that. 10 to the 8 compared to the 10 to the minus 47. I mean, there's no comparison. This thing is just minuscule. We would never even be able to measure it. There's no possible way to measure that force. It's way too small to be measured. We have a hard time measuring the gravitational force on Earth, let alone the gravitational force like that. Gravitational force on Earth is way bigger. So, that is what we call Coulomb's law, and this is specifically Coulomb's law for point charges. It only works if the charges are points and don't have any size or shape to them. If they have size and shape to them, we have to modify things a little bit, but it shouldn't get too crazy. So the next thing we talked about last time was the concept of a field. We've talked about force fields before when we talked about gravity, where a force can be exerted over a distance. It doesn't, it doesn't require contact. It doesn't require some kind of connection to something that's applying the force, like a spring or a string or something like that. The force exerts itself through space somehow, and that is the case in gravity and in electromagnetism, electrical forces. They both can act without any medium between objects or any connection between objects. And so one way to represent this kind of a force is to represent it as the forces that would be felt if you were in that region where you can feel those forces. And we call that region a force field. A gravitational field surrounds the Earth. It doesn't mean that the Earth is always pulling on something. If there was nothing around the Earth, it would never be exerting any force. There are things around the Earth, but if the Earth was out in the universe all by itself in the middle of nowhere, it would still have a gravitational field, but it would just not be acting on anything. So the gravitational field is just a representation of what forces could be felt in that region. And with electrical charge, we also have a field we call the electric field. And sometimes it's called the Coulomb force field. But the electric field is a representation, it's a vector representation of the forces that could be felt. And to represent that mathematically, we take the forces that could be felt divided by the charge that would feel them. So any charge that you put near another charge would feel a field. So we take that force, which is the Coulomb force, the equation from the last section, and we divide it by Q. We essentially erase one of the Q's from the equation, and we call that the field strength. So the field strength becomes K times Q over R squared. We replace a little q with a big Q. Big Q means we're talking about a single charge that exerts a field around itself. Little q means there's two q's that are interacting with each other and there's force between them. But they're still just charges. So it's just K times Q over R squared for the electric field. And we use this equation to calculate the strength of an electric field some distance r away from a charge Q. So let's calculate the electric field now. What is the electric field from a point charge that's 2 nanocoulombs, so that's our Q, that's at a distance 5 millimeters from that charge. So distance 5 millimeters is r, that's our r, and we plug those into our equation. It's pretty simple. The K, of course, is the Coulomb constant right there. The Q is the 2 nanocoulombs, 2 times 10 to the minus 9 coulombs, and the 5 millimeters down here squared. You get 7.19 times 10 to the 5th. It's not newtons now because we're not calculating force, we're calculating field. It's newtons per coulomb because it's force per charge. So newtons per coulomb is the units for electric field. Now, how do you calculate the force that a charge feels if you put it in that field? It's really easy. You go back to this equation and you say, well, E equals F over Q, so that means force equals Q times E if you rearrange this equation. So you just take the electric field we calculated here and multiply it by the charge you're going to put in that field. In this case, they're going to put a point charge that's negative 0.250 microcoulombs, so that's our Q that we're going to put into the field. Multiply it by the electric field we calculated up here, and we calculate that force to be, here's our charge, here's our field from the previous example, multiply it together and we get a force of 0.180 newtons, right? So a pretty strong force compared to that force in the hydrogen atom, but a charge that has a negative 0.250 microcoulomb charge is likely to be a much bigger particle, because that's a lot of charge. So that is those are the basics of electric force and electric field. Now we go on to how we represent fields. One of the biggest reasons that we talk about electric fields is so that we can represent them graphically or visually to understand a situation. So here is one way to represent a field. You have a charge Q and you represent the types, the strengths of forces and the direction of the force that you would feel near this charge. This is a positive charge. So if you put a positive charge right here next to that charge, it would feel this big force, this big long arrow of force upward. If you put it down below the charge, it would feel a force downward because it would be pushed away from it downward, and sideways and the other way and slant ways and everything else. But the further you go away, the smaller that force gets, so the arrows get smaller and smaller and smaller because it drops off as 1 over r squared, so the vectors that represent the force that you would feel get smaller and smaller and smaller. However, since these lines are further apart the further we go out, we can actually use that to our advantage. Instead of drawing a bunch of different arrows of different sizes like this, we just draw a single arrow outward from this charge, single arrows outward from this charge, and we say the distance between the lines determines the strength, the relative strength of the charge, or sorry, of the force. So if you're out here where the field lines are far apart, you don't get much strength. Further apart lines means weaker field. The field lines are closer together, it means a stronger field. And if you put a positive charge in this field, it will follow those field lines. It will move away from this charge, following the field lines, whichever way they go. And this is a very simple electric field. It's like spokes on a bicycle wheel. If this was a negative charge, what would it look like? Well, it would look like the field lines would go towards it because a positive charge. That's right, because a positive charge put near a negative charge would go towards the negative charge, right? So field lines go away from positive charges towards negative charges, and the closeness of the lines represents the strength of the field. How close they are, closer the lines, the stronger the field. The further away the lines, weaker the field. But like I said, these are very simple fields. Here's another example of a positive charge, but here's the anti-example of the negative charge, where the arrow lines are pointing in. And here's a negative charge that's different. What's the difference between this one and this one? This one has twice as many lines, so it's obviously twice as strong a field, which means it probably has twice as much charge, right? Because that's the thing that affects it. The thing that affects your field strength for a given geometry is the amount of charge. So this one has twice as much charge, so it has twice as many lines. If it had 3 times as much charge, it would have 3 times as many lines, and so on and so forth. So we have a graphical way of representing electric field, which can be quite useful in practical situations. Another thing that is useful about this is that we have once again represented force as a vector. Force is an arrow pointing in a direction, where the length of the arrow represents the strength of the field, or the strength of the force, and the direction represents the direction of the force. Well, fields are also vectors, and so you can add electric fields together. If you have two fields that are overlapping, they actually don't overlap, they actually create a new field that is the sum of those two fields. And that's what we call superpositions, very similar to the superposition of waves that we talked about at the end of the semester, where we add things together to make, add waves to make a new wave. We're going to add fields to make a new field. So here's an example of this. We're going to represent two electric fields in this picture. There's going to be one electric field going up and one electric field going sideways. We don't know anything about the charges that create those electric fields. We just know that one electric field is going up, and it has a value of 1.13 times 10 to the 5th newtons per coulomb. And one is going to the left, and it has a different value of 0.56 times 10 to the 5th newtons per coulomb. And what we want to know is, let's see, magnitude, and we want to know the total electric field that is in this region. Now they do tell us that these electric fields come from these two charges. So this charge right here is creating this electric field this way, and this charge right here is creating this electric field up this way. And they want to know the electric field at the origin from both of those fields. So what do? We add the two fields together as vectors. So this one is pointing up, this one's pointing sideways. Of course, when you add them together vectors, you make a right triangle, and then you make a rectangle, and then you draw this line from corner to corner, because it's like adding this and then putting this one up here and adding it over here, right? Remember the adding vectors graphically thing we did before? So you do that, but you should also know how to split it into components of a field, right? Which they don't do here, really. Here they don't do the components, but we should learn how to do it in components. You should know that you have x components, y components, and that this one ends up being the y component of the final vector. This one ends up being the x component of the final vector. They don't treat it that way, but it's essentially what they do. So anyway, electric field 1, they calculate the value. They don't even have to calculate the value for it. It's already calculated. Or I guess they do, because they don't tell us that in the problem originally. So they calculate the value of electric field 1 from charge 1. They calculate the value of electric field 2 from charge 2. And then they use the Pythagorean theorem to figure out what they would be added together, because it's the hypotenuse of the right triangle. And you use that Pythagorean theorem, you get the total electric field from at the origin of 1.26 times 10 to the 5th newtons per coulomb after you're done with that. And then you take the y side, or the vertical side, the vertical component, divided by the horizontal component, and you take the inverse tangent of it to calculate the angle above the horizontal that electric field is at. So you can add electric fields together, just like we've added forces together, and just like we've added velocities together, like we've added accelerations together. Any vector, adding vectors together is no different no matter what the vectors are. It's still just adding vectors together. So we can do that. And then you can have really complex electric fields like this. This is the electric field that you would get from two positive charges coming close together. And you notice something interesting. The electric fields don't cross each other ever. They turn away from each other and they don't cross. And that is always true of electric fields. Electric fields never cross. Electric fields will always push away from. Why would it be bad if electric fields crossed? What's wrong with that picture? What does the closeness of the lines represent again? If the lines are right on top of each other, how close are they? They're infinitely close, so what does that mean about the strength of the electric field? It's infinite, which is not allowed, right? We don't allow infinities in physics. There's no such thing as infinity in the real universe. In the real universe, there are actual boundaries. And there's no such thing as infinite energy, there's no such thing as infinite time, there's no such thing as infinite space. So we don't allow that. And so we just say, well, we can't have that, so the field lines can never cross. We actually make that a rule. We say, since we've never observed anything with infinite energy, or with infinite force, or with infinite field, then we're going to assume that they can never cross, and they never do. And it's led to really good understanding of electric fields. However, something else interesting happens when you have a positive charge and a negative charge. A positive charge and a negative charge don't have field lines that are opposing each other. They have field lines that are going towards each other. One is going out, one is going in. And they actually connect. This is what we call a dipole field. So in this dipole field, you have field lines that actually connect. And if you put a charge in here, it will go from one to the other. If you put a positive charge in here, it will follow the field lines and go away from the positive charge towards the negative charge, right? And if you put a negative charge in here, what will it do? Negative charges follow backwards along the field lines. And if you put it out here, it will go around in a loop here. So you start to see that you can manipulate charges very easily with electric fields. Electric fields allow you to manipulate the path that a charge will follow. Just by placing charges in different places, you can create these field lines, and those are the paths that charges will follow. So if you have some situation, some application where you need a bunch of electrons to go in this curved path like this, then this is, a configuration that you might consider to make it do that. If you need them to go away from each other, if you need electrons to get close to each other but never touch, then maybe you make this kind of a configuration, right? And many, many things are designed this way within electric fields to control the paths of charges, including things like televisions, old televisions in particular, cell phones, all kinds of things. Okay, so electric forces in biology. I'm going to suffice it to say that electric forces account for almost all of the binding of anything in biology and chemistry. Okay, so all chemical bonds, all biological processes, at their root is electrostatic and electrodynamic forces. So pretty much everything. Yeah. I'm not going to go any further than that. The thing that makes biological things interesting, and even chemistry, is the presence of these dipole molecules, or these polar molecules like water. One of the reasons water is used so much in life processes, but also in the laboratory and chemical processes, in biology classes and other things, is that its dipole nature allows it to rip things apart very easily. Because it has an electric field. Water has a natural electric field across every molecule. And so those electric fields have a tendency to pull on things, cause forces to occur. So if you pour salt into water, salt actually breaks apart in water. It breaks apart into sodium and chloride, separate atoms that were one molecule when it was solid, but now that it's in the water, it breaks apart, and that's why it dissolves in water. Salt dissolves in water because water breaks it apart. And it will dissolve permanently in water. It will just stay broken apart. It won't recombine and collect at the bottom of the glass. It just won't, unless you put so much salt in there there's no more water to break it apart. You can't oversaturate it, but if you just put a little bit of salt in water, it will break it apart and will stay broken apart until you evaporate all the water away or something. So water is very useful in that way. It's a very good solvent because it breaks things apart that are that don't have very strong bonds, that have what we call ionic bonds. But all the processes are pretty much, there's nothing that happens in biology and chemistry that's not some electrical kind of process.
So We just covered all of biology and chemistry.
That's right, we're done.
Okay.
Go pick up your credit in the front office for those 2 classes. You're good to go. All right, so now we're getting closer to the end of the chapter here. We got one more section after this one, which is pretty much homework section. The last section is doing the homework, so then we'll be good to go. So what happens though when charge encounters conductors? Because this becomes quite interesting. Because a conductor allows the electrons to move freely wherever they want to go, what will happen when you charge a conductor? Well, let's take a look at a couple of different examples. Here is a conductor, a ball made of metal, for example, put in an electric field. Here are the electric field lines. Before we put this in, the electric field was actually just straight across. How do you make an electric field that's straight across? What you do is you build a wall, and you charge up the wall with a bunch of positive charge on this side, and all the electric field lines coming away will be going straight, because there'll be like a bunch of charges next to each other. The sideways fields won't be able to cross each other, so all the lines will come straight out. So this is made that way. You have these field lines that are going straight and parallel to the right, but then you put a conductor in, and this is what happens. When you put a conductor in that electric field, all the negative charges on the conductor move to the left side of the conductor in that field. Because they're attracted, they want to follow the field lines to the left. And the positive charges, it's like they're moving to the right because the electrons move to the left, right? So you get these positive charges left over on the right side of the conductor. So you've polarized the conductor just by putting it in an electric field, right? But because you've done that, you've created a new electric field. This ball now has an electric field inside of it going from the positive side to the negative side, which actually changes the electric field around it. And the way that it changes it is all the electric field lines on the outside of the ball will always turn so that they hit the ball, so that they hit the metal at a 90-degree angle. Always. Field lines will always hit a conductor at a 90-degree angle. They will never do anything else. So it turns the electric field near the conductor. And if there's a field line that's near the conductor but never actually hits the conductor, it will just bend it, just warp it near the conductor like this. So here's another way that you can manipulate electric fields to do what you want to do. Get them to do what you want to do. So put a conductor in there. The other very interesting thing is, what happens here, what are these field lines, they're closer together now, aren't they? So the forces in here are stronger on charges. Charges are going to want to move in here a lot more because these field lines are closer together. What happens if I make this thing more and more pointy to these field lines? They get even tighter, don't they? They'll get tighter and tighter and tighter in there. And guess what? When you want your house to be safe from lightning strikes, what do you put up above it? A really pointy rod made of metal. And what do you connect that rod to? The ground, right? You connect that rod to the ground. And what happens when a really strong electric field, like a really big charged cloud, comes near your house? The electric field gets really, really strong near that rod. So it's going to really pull on electrons from the cloud. And guess what? You will not get a single lightning strike near your house. Because what it's going to do is it's going to exert a huge force on the electrons in the cloud, and it's going to pull the electrons right through the air without ever letting lightning strike. So what your lightning rod is doing is it's just sucking electrons out of the air so that that cloud never gets enough charge on it to strike your house, above your house. They may strike your next door neighbors because they don't have a lightning rod. And you see this on houses. Particularly, you'll see this on more expensive houses. Go down Leota Street and look on the peaks of the roofs of many of the houses down there. They have a whole bunch of little metal spikes on the peak of their roof. And it's not to keep birds off, although it works for that too. But they have a bunch of little metal spikes and a little wire that runs down to ground. It's a lightning rod strip. That's as simple as it gets. If you have something pointy and fairly conductive near your house, lightning will not strike your house because it's constantly yanking those electrons down because the field lines get so close together as they try to get, crowd in and get that 90-degree angle around that little tip that it just pulls the electrons straight out of the cloud. And lightning never strikes lightning rods. Never does, because it just pulls too strongly. That's kind of a misnomer. A lightning rod never gets struck by lightning. It should be called an anti-lightning rod. It should be called an electron sucking rod, right? Because all it does is suck electrons down from the clouds. Sucks them down, puts them in the ground. One of the, this week or next week, we'll break out the, well, not this week, we won't have time today, but maybe next week we'll pull out the Van de Graaff generator and I'll show you that. We'll create a lightning storm and then we'll bring in a lightning rod and show you how it just disappears. It's pretty cool. Actually, we could probably watch it online. Let's watch a video of it. Lightning.
Are you recording it?
What?
Are you recording it?
I can't hear you.
Are you recording?
Oh, am I recording? Yes, I am. Lightning rod demo. I am recording today. So let's see, how long is this one?
How many people have one of these? No, not one of those. One of these. Well, it's a nail, but what this represents is a lightning rod. How many people have a lightning rod in your house or building if you're a business? Probably not a whole lot of people. And you don't necessarily need one. But I'm going to explain to you today what they do, how they...
So here, I'm getting the point. So here he's showing how lightning strikes a ball
See
or his hand. If he brings his
that I'm
hand
getting
close
shocked.
to it,
All right, it's,
he gets
I'm
shocked.
kind of used to this. It doesn't hurt that bad once you get used to it. And I know that it's not dangerous, so it's not really that scary to me. All right, so you get the idea. Now, I'm going to hold on to this metal sphere, this doorknob here. I'm going to show you what happens with this. All right.
Can't really see it, but it is striking across there. Let me turn off the light so you can see it a little better. But it does strike across to the ball because it's a big round shape, and those field lines don't get nearly as close together on a round shape as they would on a
Shocks are
sharp
pretty
one.
consistent.
See that lightning
And,
striking across there?
The more energy that can build up around the outside of this, depending on its size, the bigger it is, the bigger this, the bigger,
Now the nail.
I can come close to this, nothing happens. All right? I can go far away, I can go closer with a nail.
So the idea is that you just have so much electric field concentrated at that tiny little point that the force on the charges from this ball, it just sucks them off without, they just do not have a chance to build up the energy, because you have to build up a lot of charge for it to strike lightning. And if you don't give it a chance to build up by just draining those electrons off, you're good to go. So, okay, so back to here. So when you have a conductor that's just on its own charged, not inside any kind of electric field, it creates its own electric field. But if it's a conductor, all the excess charge, all that charge that's creating the charge that's not balanced out by some other charge, tends to spread itself out on the edge of the conductor as much as it can. If it's on a sphere like this, it'll spread itself out nice and evenly. But if it's on some other material, it may not be so even. For example, if it's on like an egg shape, you'll get charges crowding near pointy parts and spreading themselves out more on the fatter parts, essentially. And the reason for that is an electric field thing, but it is true. That is what happens. Let's see. Here's the lightning rod demonstration where you get that really, really strong electric field at the tip. So all those charges hanging out there, and here's some nice pictures of lightning rods. So anyway, this is something that we will encounter next week in our lab, which is the building of an electric field, or the mapping of an electric field, by looking at field lines and how they encounter conductors and how field lines aren't supposed to cross each other and all that. We will use all of these things in our lab next week as we create some electric fields and then try to map them out, try to figure out where they actually are. So that's kind of what we do with that. Now, the final section, which is applications of electrostatics. The Van de Graaff generator. So this is how it works. This is what's on the inside. I think I explained it in basic detail before, but now I'll explain it in more detail. On the inside of a Van de Graaff generator, you have these two wheels, usually one of them connected to a motor, usually the bottom one. And between the wheels, you have a belt that's going around and around. And you put a comb, a metal comb, near the belt on the bottom. It doesn't even have to be on the belt, just near the belt, and make pointy ends there so you get a really, really strong electric field. Connect that comb to ground where it can just suck up all kinds of electrons. It has all, well, actually what it does is it doesn't suck up electrons from ground, it sucks electrons off of the belt is what it really does, because the metal has a tendency to want electrons. So it pulls electrons off the belt and leaves the belt positively charged. Excuse me. And then, as that belt goes up towards the top, it encounters the sphere, and you put a comb on the top side as well that is connected to the sphere. And because the top side is not connected to ground, there's a big insulator in between, like made of glass or plastic or something in between. Because the top is isolated from ground, it actually will give electrons to the belt. So it becomes positive, more and more and more positively charged, and the belt goes back down, neutral on one side. So this side the belt is neutral, this side the belt is positively charged. And as you do this more and more and more and spin this belt around more and more and more, you just get more and more and more and more and more charge built up on this sphere. Now how can you make, what two things are you going to need to do to this thing to make it a bigger charge collector? If you want to collect more charge on this sphere, you're going to have to do two things. Can you guess what two things they are?
Move the belt faster.
The speed of the belt doesn't matter, because what's going to happen is you're just going to fill up this sphere and then you won't be able to charge it anymore.
So you need a bigger sphere.
Okay, so you need a bigger sphere. That's one thing. But what happens once you fill up the sphere? What happens with one of these things when you fill up the sphere? Once it gets to its maximum charge, it does something to get rid of excess charge. Lightning strikes, right? So you have this big sphere, but then eventually it strikes, and what does it strike?
The outer edge, I don't know.
So the strike comes from the outside of the sphere, and where does it go? Where does lightning go from a cloud? To ground. So if we're going to make this bigger and we don't want it to strike, what do we need? What else do we need to change?
You need to disconnect it from the ground.
Not disconnect it, because that's what charges
You
it.
gotta make the distance bigger.
The distance needs to be bigger. We need to make it taller. So the two things that you do to make these things bigger, to make them charge bigger, is you make them taller and you make the sphere bigger. So I have two of these things. I have a little one with a little tiny sphere, and it's only about 18 inches tall. And then I have that big one that's about 3 feet tall, and the sphere is about 3 times bigger, 2 times bigger. The ones that, let's see, if you go to, what's the name of the place? Chicago's Van de Graaff. The National Lab there, what's it called? What's the name of, I can't remember all of a sudden. It's the, no. What's not argon? Shoot, I can't remember it. Fermi, there we go. Fermi Lab. Fermi National Lab, Van de Graaff. So if you go to Fermi National Labs Van de Graaff generator, they use this thing to accelerate particles up to pretty much the speed of light, almost the speed of light. And this is what theirs look like.
I want.
Yeah, totally awesome, huh? I've seen those. They're huge. And you can put them on their sides too, but if you put them on their sides, of course, they're close to ground. So what they do is they put them in a vacuum chamber, which isolates them from ground even more. Then you have ones like this. That's actually the one that no, that's the one at Oregon. But I've seen the one that's like the one that I've seen that looks very similar to this at Fermi Labs. It's that's it right there. Isn't that a great Van de Graaff generator right there? Very cool. Now, here's a really cool picture. See, these Van de Graaff generators are fully charged up, but these people are inside this cage and they're perfectly fine. I mean, the shock that comes off these is big enough to kill. It's huge.
It's like.
But they're fine. They've got their kite. They're flying their kite, you know, and they're fine. Why are they fine?
Cage, bars, Faraday cage.
It's a Faraday cage, but what the heck does that got to do with anything?
But the small bars would act like lightning.
Nope, it's not that they act like a lightning rod. But you're on the right track. It's that they are made of what? They're made of a conductor. And what did we say about the charge on a conductor? If you charge up a conductor, where does that extra charge always go? It's far away from the rest of the extra charge, and it stays on the outside of the conductor. So if you're inside a metal cage in a charged environment, where is all the charge from that environment? On the outside of the cage. And where are you? Inside of the cage. So you're fine. Don't grab the bars. Don't put your hands around to the outside of the bars. That will hurt. Okay? But you can touch the inside of the bar just fine. You can touch the inside of your car in a lightning storm just fine. Just don't open your car and get outside. Put your hand outside in a lightning storm. Right? It's when you get outside the car at the gas station that you're in danger of making a spark with whatever. Right? It's not when you're inside the car. When you're inside the car, it's fine. Why does your car get charged up when you drive down the highway? Rubber on road. There's an electron transfer. The road and the rubber have different electron affinities, so electrons want to go from one to the other, and both things end up being charged up. Who cares if the road's charged up? But you care if your car gets charged up.
Wait a second, go back.
Go back where?
What the Van de Graaff, they take in a lot of electrons, right?
Actually, what they do is they are actually void of electrons. They're having electrons taken off of them, so they're positively charged. So these are positively charged here, and this cage is going to get negatively charged on the outside because it's going to be a track well on one side and positive well on the other. But the outside of it is going to get a lot of charge on it, a lot of excess charge.
It goes back to one side of the bars are.
Yeah, so on the inside of the cage, though, there's no excess charge. It's all neutral on it. It's all neutral on the inside of the cage. It's the outside of the cage that gets polarized. So let me draw it on the board really quick. So let me turn on my camera. Okay, so and if I do this, this is going to look backwards, but I just won't write any letters, right? I won't write any words.
You might
So-
want to put the light on.
Oh, it's really visible here. I'm not worried about it up there. So, but here's your positively charged Van de Graaff generator, right? And so it's creating this huge field, this electric field E that's pointing away from it. And here's your cage, right? So it's got this hugely positive field pointing this way. That means electrons are going to want to be attracted to it. And protons or positive charges are going to want to be on the other side from it. They're going to get pushed this way. But only on the outside of the cage. The inside of the cage is completely neutral. Inside here, you're completely safe. And the reason for that is because excess charge tries to get us far away from other excess charge, and so it stays on the outside of the cage. The inside of the cage stays neutral, and so you're fine. And that's particularly true if you ground that cage, ground the inside of that cage. Because then any excess charge that gets in there, even if you have moving charges,
So
then
that'll
you're
make your
safe.
Faraday cage, right? So there'll be no more protons at the top.
There's still protons up there, there's just extra electrons. So electrons
So all your
moved,
say all your electrons from the bottom. go
moved
to
from the bottom to the top. So
But
the
since
bottom
your
is positive.
protons can't move,
So the bottom becomes positive because it's lost electrons. The top becomes negative because it's gained electrons. That's correct. But the overall idea is that inside the cage you're safe. Now I do this all the time with this is one of the demonstrations I can show you next week. Is
so protons don't move, right?
yeah, protons don't move around very easily.
Right. But in the Van de Graaff generator, they're just taking all the electrons.
They're just
out.
stripping the electrons off of the Van de Graaff.
So,
That's right.
okay, so they're not adding
No.
protons. They're
No, what's going on is electrons are moving down this side from here, and on the other side of the belt there are no electrons on the belt. So as the belt
and
goes
that's
up one
because
side,
of the grounded brush.
that's right. So as the belt goes up one side, it has no electrons, and then it steals electrons from the top and takes them down the other side
Okay.
and drops them off at ground. And the Van de Graaff generator can create huge amounts of electric field. Huge. All it depends on is how tall you build it and how big you build that ball on top.
And the lightning, as you see, is the electrons jumping from the Faraday cage to the.
That's right. And if you see lightning from ground up to the generator, it's actually electrons jumping from ground to generator. That's correct. It's the opposite with clouds. Clouds get negatively charged, I believe. So, is that correct? I think it is. I think clouds actually have a negative charge on the bottom of the cloud and positive on the top. And so lightning from clouds is I believe is the movement of electrons from cloud to ground. But with Van de Graaff generators, it's from ground to generator. So it's kind of the opposite.
Yeah, that makes perfect sense. Yep.
All right, so if you ever have a chance to go see this museum at Boston, so this is in the Museum of Science in Boston, the largest Van de Graaff generator. It is a cool show. You actually walk into the room inside of a Faraday cage on a walk. There's a walkway with a Faraday cage around it, and it's big enough that you can't get anywhere near the bars. And lightning strikes these demonstrators up here, and they're doing all kinds of stuff. They're throwing stuff out into there to get it charged up, and you watch things get zapped by lightning and all this cool stuff. And your cage around you is getting zapped by lightning, and music and lights going. It's a really cool thing. It's certainly worth going to see. I have not actually been to see it. I've only seen it video. So.
Whenever they put it in a vacuum, doesn't that change the ionization of it?
If they yeah, it does, and that's the whole point. If you put it in a vacuum, it lowers the ionization threshold. Actually, it raises the ionization threshold so that you can increase the amount of charge you can put on a Van de Graaff. But in a vacuum, it's done for experiments. It's not done for observation. So that's done to increase the amount of energy you can build up.
Vacuum, they do funny things to everything.
Yeah, well, vacuum essentially makes it very difficult for the charge to jump off. It doesn't have anywhere to go. It doesn't have anything to move through like air. So vacuum allows you to build up a bigger charge. Eventually, electrons will jump through a vacuum as well, but they can't travel on another atom, so they have to do their own jumping. Makes it a much better.
More violent too, probably.
Yeah. Here you can kind of see this a little bit better. Oh, that's a different one.
How do you neutralize, how do they neutralize using charges in places like the ISS where there's no path?
So where?
International Space Station. They don't really get a lot of buildup of excess charge there.
There's no friction.
Because there's no friction. They do get some, but not much. But static electricity can be captured as well, and so I think that they actually capture it and use it.
Electricity.
Yeah, so they capture it in capacitors,
Yeah.
and then they use it as electricity. But there's not a lot up there. But they can. That brings up another interesting thing. You can actually create propulsion doing the same thing. So you can actually create your own static electricity and then draw things through that, through electric field, and then propel a spacecraft that way. And that's electrostatic propulsion, and they've been working on that for years, and they're actually using it now. We actually built one when I was in college, my senior year. We built an electrostatic propulsion device. We took apart an old television, and we hooked up 17,000 volts to this little kite made of balsa wood and tinfoil and wire. It was essentially a capacitor made of balsa wood, and we actually got it to fly. It was like a UFO, and we demonstrated it in class, and then it lit on fire in the middle of our demonstration. It was so awesome. But we got like the best prize for the coolest demonstration. We made our own electrostatic UFO device. But they use those on satellites all the time now, where they create essentially this huge electric field inside of a cylinder, and anything that comes near it out there in space gets attracted into this, gets polarized and pulled through. And as it gets pulled through, it acts as propulsion. The spacecraft goes the other direction.
And then all the positive and negative when that piece is going through, as it's going through, it flops.
Yep.
It spits out the other.
That's correct. That is correct. That's a very keen observation. Not many people catch that. But when something is polarized by a field, it actually rotates the opposite direction of the field. And that's what causes it to propel through. And then you're able to create propulsion using just electricity, and you don't lose any energy by doing it either. It's a very low energy use propulsion device. It doesn't. Well, no. All you have to do is charge something up, and charging something up is not difficult to do. And holding the charge doesn't require any energy. You just charge something up and leave it there, and it will propel you. It doesn't provide a lot of acceleration because there's not a lot of stuff out in space to pull through your propulsion device. But every little bit counts, and you can use it to turn satellites and to make corrections and things like that. And if you leave it on long enough, you could actually use it to go very, very quick, very, very fast. It would just take a long time. So it's one of the devices. And isn't that cool? That's the main building at Fermilab. It looks like a great big pie symbol. And all the power lines in front of this building, I don't know if you can see them, but there's a bunch of, you can't really see them. There's a bunch of power lines that are all shaped like pie as well. That's their little assault on the ordinary, I guess. So anyway, that's the end of the chapter for us. We do want to go over the homework and know how to apply these things. Let's take, well, I think I'm okay to keep going. I wasn't feeling good about an hour ago, but I'm feeling a lot better now, so we'll just keep going until I throw up.
How about here in chapter 19, and let us work on homework and questions? Or you answer our questions.
Well, one of the reasons that I want to go over the homework is because people who are watching this recording are not going to have the benefit of my office hour, right? So if we get going on a problem that's really complex during the office hour, I might turn on video again and record it for them. But for the most part, I won't record my office hours necessarily because it'd be just a lot of, video of you guys working on your homework. But we'll definitely take some time right now to look at the homework really quickly. So let's do that. Chapter 18 homework. We start off here with the triboelectric series, right, which shows essentially how much things like to lose or gain electrons, right? So dry skin tends to really like to lose electrons, and Teflon likes to gain electrons. So on a dry day, when your skin's nice and dry, don't wear Teflon, because the Teflon will get really, really charged up with your electrons, and your skin will get really, really uncharged with electrons, and so your clothes will stick to you. Does that happen with your clothes sometimes? And it usually happens with what kind of clothing? Artificial polyesters, which are like Teflon. Teflon and polyester are made of the same kind of stuff. Made of these long polymer molecules, and those things really like to suck electrons off things. So how do you counteract it? You moisturize. Because dry skin and wet skin behave very differently. Wet skin doesn't tend to want to, wet skin's usually more kind of up here. It tends to want to take electrons as well. And so they won't do anything, they will do less. One thing that you can do on a wet day, on a day like that, is just put some water between your shirt and your skin, and that will help. But you can also use, a moisturizer of some kind, but that will always help. Same thing with your hair on a dry day, right? Human hair has a tendency to lose electrons, so if you comb your hair with your Teflon comb every morning, which most people use a hard rubber comb or a plastic comb, then you're going to get static, right? So essentially, the further apart these are on the list, the more likely they are to charge each other. The closer they are together on the list, the less likely they are to charge each other. It's that simple. What was your question, Scott?
So the tend to gain electrons and tend to lose electrons, right?
Yep.
So if you had steel and rubber, right?
Steel and rubber.
Alright. Since your steel is closer to the tend to lose electrons, it's positive, and the rubber is negative because it tends to gain.
So because steel and rubber are fairly close together on this chart, they're not going to transfer electrons very, very well. If you rub steel and rubber together, there's not going to be much transfer. You'll get some because they're not exactly the same, but you're not going to get much. And in fact, that's what happens when you're with your car on the road and with the Van de Graaff. You don't get much, but that's why we turn the wheel really fast.
Yeah, but which one would be positive and which one would be negative?
Well, which one would be positive, which one would be negative? The rubber would be the more tendency to gain electrons, so it would be negative, and the steel would be positive. So the one that's on top in the series tends to be more positive. The one on the bottom tends to be negative. And that's the whole idea of the electron affinity, is this triboelectric series.
Is that printer in that room wireless?
It used to be, and I'm trying to fix it again, but it's not now.
Because it just said I could print on it.
Well, then try, and we'll see if it works.
Well, if there's a paper.
Okay, correct order of steps of induction. So this goes back to bringing that charged object close to something and then, grounding it and all that stuff. So you just have to go look at the place in the book where they talk about induction and try to get the steps matched up in the right order. I'm not going to tell you the steps in the right order because that would... also realize that you have to realize that they've got your steps out of order over here. So you got to be careful because they're trying to make it harder to cheat, I guess. And then terms of definitions, right? Polarization, which one is that?
Separation.
Yeah, polarization is just separation of charge on an object, right? I'll let you do the rest on your own. So here they have 3 microscopic latex spheres. So latex is rubber. And they're sprayed into a chamber and they become charged. And they're charged with these types of charges, 3e, 5e, and negative 3e. So what's the total charge? Positive 5e. That's all I'm going to tell you about this problem. Okay? The total charge at the beginning is positive 5e. E means that little e, script e in electrostatics is the charge of an electron. So 1.6 times 10 to the minus 19. So this is positive 3 electrons, positive 5 electrons, or 3 protons. You can think of it as 5 protons. And negative 3 or 3 electrons. So the total charge is positive 5. What does it have to be at the end? I'll leave it at that. If A, B, and C all have the same charge, they will pull together. True or false? If A and C are negative, B is positive, B will be pushed away from A and C. True or false? I'm not going to answer these questions. I'm going to let you do it. They're mostly logic questions. So what is the sign of charge A in this problem? Field lines go away from positive charges and towards negative charges, always. So the field lines are going away from A, it's a positive charge.
B is negative.
Yeah, I'll let you figure out the rest. All right. We have massive positively charged particles When we say massive in physics, we don't mean they're huge.
They have mass.
We just say it just means they have mass. And that mass can be any type of mass. They have mass. They're positively charges and they're initially held at a fixed distance apart. When they are moved farther apart, the magnitude of their mutual gravitational force changes by a factor of n. Which of the following indicates the factor by which the magnitude of the mutual electrostatic force changes? So if they're moved apart and the mutual gravitational force changes by a factor of n, how is gravitational force related to distance? It's 1 over r squared, right? So if the gravitational force changes by a factor of n, how does the electrical force change? What is electrical force related to? It's n again, right? Because they're both affected the same way. Gravitational force changes as 1 over the distance squared, but so does electrostatic force. Electrostatic force changes by 1 over the distance squared. So if the gravitational force changes by half, then the electrostatic force will change by half. Because they're both affected the same way when you change distance. So that's a bit of a trick question. Because they're not talking about distance, they're talking about the gravitational force change. The gravitational force
They're
changes.
talking about positively charged and then they go to gravitational force.
Right, so what they're saying, what we've got here, and let's take a look at this on the board really quick. Where's my eraser?
And I got
Lost all my
I got
erasers.
some of my Kleenex.
I'm wearing a fleece jacket. And it's gray. Nobody will ever know. Okay, so we have these two charges. They have a force between them that is an electric force, that is this repulsive force, right? This electric force. One of them feels a force this way, the other one feels the same force the other way, right? That's the electric force. I have to draw it backwards for the people on. But we also have a gravitational force between them. A force that is a gravitational force. And the gravitational force between them is pointing outward. No, it's actually pointing inward.
Well,
Right?
it's not the same equation.
No, it's not the same equation, but they're both forces. We'll make them different sizes so that they're different things. They're not the same equation, but each equation has a 1 over r squared dependence.
Right.
Right? So if we move these two things out twice as far apart as they were before, the gravitational force will change by 1/4. It'll be 1 over 2 squared, right? But this one will also change by 1 over 4, because it's also a 1 over r squared thing.
That's if radius is 2.
And that's what they told you. They said the n, the amount that the gravitational force is changed by is something n. So what is it going to be for the electrostatic force? It's also going to be n, because they change the same way. They're not the same force, they're not the same equation, but they both change the same when you move things further apart or closer together. So that's what the question is
So
talking
the
about.
n equals your 1 over r squared.
That's right. N equals 1 over r squared. It is dumb. Maybe it's a dumb way to ask a question.
Yeah, it's really dumb.
It's a
But if you're smart, you can answer it. Right? Smart people can answer dumb questions. Dumb people cannot answer smart questions, or dumb questions, or any question at all.
because they cannot speak by the definition of God.
That's correct. Okay. So, happens force between charges. That's the same kind of question. It's just a
You're wrong.
thing. Okay, pretend the circles are bodies of mass with the same mass holding the same amount of charge, sign of the charge shown. So each one of these circles has the same mass and the same amount of charge, but the sign of the charge is different. Distance between them is shown, that's the same also. What is the algebraic expression for the magnitude of the net force on M3? So what they want is an equation that includes M1, well not necessarily M1, but they want an equation that is like force equals Q1 Q2 over D2 squared or something. You want an equation like that to calculate the magnitude of the force. The problem here is that you're going to have a force from M1 on M3, so you're going to have to calculate that force, and then you're going to have a calculate a force that is from M2 on M3. You have one from M1 and one from M2 on M3, and those forces are going to be actually in different directions, and then you have to add them together to get a total force. One is going to be a negative force too, because one of them is going to pull this thing to the left, and one of them is going to push it to the right. So they're going to be in opposite directions. One's going to be a positive force, one's going to be a negative force. You're going to have to add them together to get a total magnitude of a force. So that one's a little tricky. But it's still just Coulomb's law. Coulomb's law from two different charges added together to make a total force, and it's not going to be a number. It's going to be in terms of Q1, Q2, Q3. Well, they're all the same Q, so it's going to be in terms of Q and M and D. Like the distance from M1 to M3 is 2 times D, right? So that's the distance for that one. You've got to remember to square the 2 and the D. Heck, let's do this one together. Let's actually write this one out. I'm going to switch to my Zoom account instead of using this other thing so that we can see the here we go. Okay. All right. So we have 3 charges. We have charge 1, charge 2, and charge 3. They all have the same mass. They all have the same charge Q, except that I'm not going to necessarily use the same charge signs. One is positive, one's negative, another one's positive, another one's negative, whatever. So I'm going to use different signs than maybe you have, but that's okay because I don't think they're all the same. But anyway, so we have this situation, Q1, Q2, Q3, and they want to know what is the force on one of these charges compared to the other charges. I'm going to do the force on 1 compared to 3. So we want to know all the forces on charge 1 with these other ones. So we start off with the force that's caused by charge 2 on 1. We'll call that force 2-1. And that force, the first thing I'm going to do is I'm going to figure out what direction it is. We're going to call this direction the negative direction, and this direction the positive direction. We have a distance d here, and a distance d here. Force of charge 2 on charge 1 is going to be the K constant, Coulomb constant K, times charge 2, Q2, which is just Q, charge 1, which is also Q, and then over the distance squared, which is d squared. And which direction is it going to be? This one is going to pull on this one because this one's positive, this one's negative, it's going to attract it, right? So the force is going to be to the right, which is positive, so it's going to be a positive force.
So if they're attracting, they're positive?
No, if it's attracting it, then it's pulling it this way, and that's positive direction, right? Because it's attracting it, it's pulling it to the right. To the right is my positive direction.
So you're considering the one in the middle as your anchor?
No, I'm just saying that this one is pulling on this one. I just want to know what is the force on this one, and this one's pulling on it. Yeah, it is, but I don't care about that. I only care about the force on this one. It's asking the force about this one. Your question might be asking what's the force on number 3. Mine's going to ask what's the force on number 1. Whatever, right? So I'm just calculating the forces on 1. I'm not calculating the forces on all of them. I just want to know the forces that are acting on this one. The forces that are acting on charge 1 are the forces from this one and the forces from this one. So I'm calculating first the force from charge 2, and that's K times Q over D squared, and it's positive because it's pulling charge 1 this direction. Okay? So that's my first one. Now, let's do the force from charge 3 on charge 1. Force 3-1 is the force that charge 3 exerts on charge 1. So this one is a negative charge, so it's going to do what to charge 1? If they're both negative, what kind of force we're going to get? We're going to get a repulsive force. So which direction is 1 going to go from charge 3's force? It's going to go this way, right? If charge 3 is negative, charge 1 is negative, charge 3 is going to push charge 1 to the left. So that's going to be a negative force. And then it's K times the charge Q times the charge Q, since they're both the same charge. Same amount of charge anyway. And then I divide by the distance. What's the distance between 3 and 1?
Two.
2 times D. Make sure that you put the 2 and the D inside of parentheses and then square them both. So 2 times D squared. Now the total charge, F1, the total charge on F1 is equal to the charge, the total force on F1, not charge. The total force on charge 1 is force 2-1. It's very difficult to write here. Plus force 3-1. I need to buy a little tablet or something that can write on this for me here. Force 2-1 is K QQ over D squared. Force 3-1 is negative K QQ over 4D squared when I multiply that out. Right? I find a common denominator by multiplying both top and bottom of this first fraction by 4. And this ends up equaling 4 KQQ. That's a G. Minus 1 KQQ. Goodness, that's ugly. Over 4D squared. And my answer ends up being 4 KQQ minus 1 KQQ, so that's 3 times K times Q all over 4D squared. Now yours will be a little bit different, but that's the idea. The idea is calculate the force from one charge on the one that you're interested in. Calculate the force from the other charge on the one you're interested in. Make sure you get the directions correct. Add them together to create your overall charge, and then plug that number in for your answer, and you're good to go. Now the real kicker is that you can do this in 2 dimensions and 3 dimensions as well. It doesn't have to just be on a line. You can have 3 charges out in space in a plane. And then you have to consider the forces in components.
Where's the 4 come from? 4KQQ.
Because I found a common denominator between these two here. This one has a 4D squared in the bottom because it's 2D squared, right? So it ends up with a 4 times D squared. And then I found a common denominator by multiplying 4 over 4 right here. Keep forgetting I need to find a good drawing board that I can use to do my whiteboard stuff on my computer.
They make mouses that are just pens and pads.
I know they do, and I need to just find a good one. I think I can do it with an iPad, and I've got several iPads. So I think I can do it with an iPad, but I've just not figured it out yet. I tried to do it with Zoom because Zoom is supposed to be able to connect to your iPad, but I couldn't get it to work. I think my iPads are too old. Need some new ones. Okay, so that is question 9. Let's move on to some more questions here and see what we can learn, see what we can see here. So this one's about direction and calculating using Coulomb's law. We just did an example of that, so I'm not going to go into it. Another one is just Coulomb's law again. I mean, these are just simple Coulomb's law questions. This one is just picking a direction, but you have to remember that different forces are going to add together and do different things. Same thing here, it's just a direction thing. Another Coulomb's law problem, except in this one, they tell you the force, and you're supposed to calculate Q2 in terms of those constants, so you're rearranging the equation. They want to know how many electrons are missing from each other. So here you have to calculate the charge, and then from the Coulomb equation, and so you're rearranging the equation to solve for charge instead of. And in this one here, you're going to rearrange the Coulomb equation to solve for Q, but remember there are two Q's in that equation, and you're going to split the amount of charge between the two Q's. So you're going to calculate a total amount of charge and split that between two different Q's. So make sure that you, well, you should probably actually just include both Q's, because then you'll solve for Q and be done. But anyway, just realize that each charge will have that amount Q of electrons of charge remaining. Then you'll be able to calculate the number of electrons by dividing by the number of the amount of charge per electron. Remember, the charge per electron is much smaller than the actual charge that might be there. And then they have a hollow metal sphere with this amount of charge on it and a radius of 0.7 meters. They want to know what the electric field is at a distance from the center of the sphere, inside and outside the sphere. Now that's kind of interesting. We didn't really talk about that in detail. We didn't talk about it explicitly. But if you have a sphere, let's go back to our whiteboard here. Excuse me. If we already said that if you have a sphere and you charge it up with charges, where are the excess charges going to be again?
Yes.
On the outside of the sphere. And what does that mean is on the inside of the sphere? Neutral. So if you're inside the sphere anywhere, what kind of electric field do you see? Well, these charges out here can still exert a field inside. They'll still point a field inside, won't they? But guess what? The field from this charge will do what to the field from this charge? What's that?
Your protons go to the inward arm, your electrons go to the outer edge, so there's more protons on the inside.
Well, yeah. Well, no. On the inside, you have protons and electrons that are canceling each other out. But these electrons that are on the outside of the sphere are all creating fields that are pointing towards each other. And if you have two electric fields that are equal and opposite, what do they do when you add them together? Zero. So inside of a conductor, in an electrostatic situation, no matter what, it doesn't even matter if it's a sphere. It turns out it works for any shape. Inside of a conductor, even if it's hollow or solid, in an electrostatic situation, the electric field is always zero. So what does that do for you here? If the radius of your sphere is 0.7 meters, what's the electric field at 0.21 centimeters from the center? 0. 0.42? 0.63? 0.84? Not 0. At 0.84 and 1.05, you can actually treat, when you're outside the sphere, you can treat the sphere as if it's a point, because it will behave just like a point particle if it's a sphere. That is not true for any shape, that's only true for spheres. But a sphere outside of it has an electric field that points out of it like wheels on a spoke, just like a point particle at the center of the sphere. So if you're at 0.84 meters from the sphere, you use that as your R in the equation. You use the charge on the sphere as your Q in the equation for electric field, and you just calculate the field.
So you wouldn't use 0.14 as your...
Nope, you don't take the difference because it behaves as if the point charge was all at the
Yeah,
center.
but don't you gotta change your micro to 10 times 10 to the 6th or whatever to make it?
Yeah, you definitely want to change your charge You want to use negative 90 times 10 to the minus 6 for microcoulombs, for sure. Yes. So your charge is negative 90 times 10 to the minus 6. But that's the only thing you really have to move around in that.
And then you gotta use the distance that they give you, right?
That's correct. But any distance that is less than your radius, electric field is going to be what? 0. Any distance that's greater than your radius, then you just calculate. That's the equation that looks like in the electric field section. If you go back to electric field right here.
That's the one where there's just 3 letters.
It's the electric field. It's calculated by taking the Coulomb constant times the charge divided by R squared. Right there. That's there's two electric field equations. There's this one, electric field equals force divided by charge, and then there's electric field equals Coulomb constant times Q over R squared. That's what you want to use when you're trying to calculate the field from the charge. If you're dealing with forces in fields, then you use this one. So that's number 16. Number 17 is another is an application one where we're using cathode ray tubes, which is how old televisions were made. And in this case, you have these plates, the plates on the left, and you have the plates on the top and bottom here. And I think actually they only talk about these 2 plates here. So what happens is you have electrons being created. You have electrons being shot off of this plate, and then they are accelerated towards this plate. And so you have an electric field in between these 2 things, you have an electric force in between these 2 things, and they want you to calculate some things. So you have, they have an electric field of 1200 newtons per coulomb, and they want to know what is the force on an electron between those 2 plates. Well, if your field is 1200 newton per coulomb, and you want to know the force, you go back to this equation for force and field, and you rearrange it for the force, and you get force equals electric field times charge. So you just take the electric field that they give you, which is the 1200 newtons, times the charge of an electron, 1.6 times 10 to the minus 19 coulombs, and that will tell you the force that it feels between those 2 plates.
So you use the constant.
That's right. You just use electric field, you just 1200 times the charge of an electron, and you're done. Then, once you find that force, you can calculate the acceleration of the electron from Newton's second law. Force equals mass times acceleration. Mass of an electron, force that they just calculated, and then calculate the acceleration.
That doesn't go to be stupid.
What's that?
It's going to be large.
It'll be a very large acceleration, yes, because the mass is so tiny. Then, if it starts from rest at the negative plate, and it accelerates all the way the 0.06 meters to the positive plate, what is its velocity going to be? That's kinematics. Final velocity equals initial velocity times acceleration times 1/2, 2 times acceleration times distance. It's a kinematic equation, look it up. I can't remember exactly what it is, but it's something like that. There's a kinematic equation for that, and you're good to go. How much time will it take for the electron to travel through the plates? That's a kinematic equation. You look it up in the last semester and you plug it in and you go. It's pretty simple. It's going to be cooking when it goes across there. 17, you usually have about 17,000 volts across these things. It can really accelerate things really fast. It's enough energy to light some balsa wood on fire, I can tell you that much. Okay. Then here is the doozy. This one, you have charges in a 2-dimensional configuration. You have to calculate now forces in 2 dimensions, electric fields in 2 dimensions, components. The force that this thing feels from these 2 things might be off in this direction. So you're going to have to split it into an X components and Y components. And I'm going to leave it for you guys to try. And if by the end of, are you guys all going to stay for the office hour and work on homework? You have class in 20 minutes? Okay.
I gotta go
Okay, so what we'll do, do you guys have the next 20 minutes to work on this? Are you available? Okay, so maybe we'll save this for our last thing that we do here for a few minutes.
No, we saved it 20.
But I'm not going to do the whole problem. I'm gonna show you the basics of it and let you guys work on it. But you know, I'm not that nice. Then here's another one that's a nice one where you have these charges. They don't tell you anything about them except that they tell you that sphere B is definitely negatively charged, and you have to figure out everything else. I'll leave that to you too. And then this one is another similar one to that, where they tell you some they tell you some information, and then they tell you that we're going to bring these and touch them together, and then we're going to bring them apart, and then we're going to bring them close to each other. So you have to figure out where the charge is going to go. And another thing that you should know is that if you have two objects that are the same, like spheres, and you touch them together, the charge will distribute itself equally to both items. So if you have one charge that has 10 coulombs of positive charge on it and another one that has 0 charge, and you bring them together and then you take them apart, they'll both have 5 positive. If you have one that has 5 positive, one that has 2 negative, and you bring them together, they will equal out. You'll get 5 positive plus 2 negative, which will equal 3 positive total. And when you bring them apart, they'll have 3 positive total on both, on between both. So it'll be 1.5 on each. Does that make sense?
always moving towards balance.
You'll always get a balance of the total on each. Okay? So, and remember, measuring coulombs is not measuring number of electrons, right? So if I have 5 coulombs here and 3 coulombs here, that makes 8 coulombs. That's not 8 electrons. You can have 3.5 coulombs. You just can't have 3.5 electrons, right? So you just got to remember that. That's easy to mix up. So let's go back to our mother of all questions. This is the big one for this chapter. How do we do this? So again, I'm not going to really do this exact problem. I'm just going to go over here and do something similar to it so you can see how it's done. Why? Because that's mean. And I like to be mean. Okay, I wish they had like well, they do have a circle drawing tool. I'm going to draw a circle. Whoop. 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 Okay, so I have my, I can even use letters here. Q1, and I have my Q2. It's much nicer than me writing things. Q3. And I'm not going to say what they are or anything. I'm just going to show you what we've got. And actually, I think I'm going to move some things around here. Whoops. Can I move it? Maybe not.
I think you can if you go grab one of the dots. You just need a much bigger.
There we go. Okay. This thing just doesn't like me. Okay, so Q1, Q2, Q3, they're over here, and they're going to be on this axis we're going to create here. Here's my axis kind of thing here. This is kind of like my XY axis. Move this one down, maybe. Okay, so my 0 point on my axis is going to be right here. This is going to be 0, 0. Right down here at this corner. And this is going to be at some distance upward in y and x, and this is going to be at the same distance upward in y, but a different place in x. and so on and so forth. So this will be at, let's put this one at, it'll be at x comma 0. This one will be at x comma y, and this one will be at 0 comma y, right? That's where they'll be at. So those are the coordinates of these objects, and they each have different charges, Q1, Q2, Q3, so hopefully that's somewhat understandable. It's a little more time, I would make it cleaner. But what we want to do is we want to figure out the force on one of these due to the other, or the field at some place near here. We can do both of those things. What I want to do is I want to calculate the field at the origin. I want to calculate the field down here at this point down here at 0 comma 0. That's the first thing I want to do. So remember, to calculate field is calculated by using this equation, K times Q, where Q is the charge that's making the field, and we divide that by R squared. Right? That's my equation for electric field. And what I need to do is I need to calculate the electric field from each one of these things separately, and then add them all together to create the total field. But because we're in 2 dimensions, because we have something going to the left, something going down, something going downward to the left, we're going to have some issues. Also, I want to add to this mess that we're going to have a charge up here, Q2, which is going to be negative. Can't see that. Let's see. Select this guy. And how do I do the text inside this box? I don't, apparently. Anyway, Q2 is going to be negative. I'm going to consider the charge here, Q2. Put a negative sign right in front of it. There we go. Q2 is negative. And that's fine. But what we need to do is we need to calculate this, but we need to have an X thing, and we need to have over here maybe a Y thing. And we need to do these 2 things separately. So forces that are in the X direction are going to be calculated here, forces in the Y direction calculated here. Then I'll add all the X direction forces, and I'll add all the Y direction forces, and I'll create an overall vector at the end. Well, the force from Q3 on, well, not the force, but the field, I wrote force up here, but that should be field. That should be E, not F. And I can't change it, dang it. How do I fix that? Let's delete that and try it again. So the field, the electric field, it's E, not F. Electric field equals K times Q divided by R squared.
I'll check the recording.
Sounds good. So I'm going to calculate all the E fields in the X direction here, all the electric fields in the Y direction here, and then I'll add them together to make an overall electric field. This Q3 is only going to make an electric field that's in the X direction here because it's lined up with the origin here. And remember that electric field and electric force act along these lines between charges. So the electric field from 3, which we'll call E3, will equal K times Q3, where's my Q? Q3, divided by the distance between Q3 and the origin squared. The distance between Q3 and the origin squared is X. So it'll be X squared, right? So there's my first one. My second one will come from Q2. Now Q2 has 2 electric fields. It has an electric field that is pointing down this way.
Should we do Q1 next?
I'm going to do it from Q2 next. Undo. So from the electric field from Q2 is going to be pointing down towards the origin like this. Okay? So that means it has a Y component and an X component. Its X component looks kind of like this. Dang it. It goes from here out this way, the X component, its y component looks like this. It goes from here down this way, right? So it has two parts to its vector, one that goes to the right or the left, and one that goes down. So the only one that I'm interested in is the one that's pointing in the x direction, in the x dimension. So I'm going to go ahead and figure out that one. That e, we're going to call that E2 in the x direction. And because it's pointing in the negative direction, it's going to be a negative, and because it's, well, we haven't figured out that yet for the other one either, so we'll wait for that. E2x is going to equal to k times q2 divided by the distance between this point and this point. Well, the distance between this point and this point is not x and it's not y. It's actually x squared plus y squared square root, right? So we have to take the square root of x squared plus y squared.
And square that.
And we just take this. No, we just take the square root of it.
Right, but then we have to square this.
Let's see. Yes.
So the square root.
So it's just that. It's the square of the square root of the square root of the square. So we square root it when we're calculating it, but then we square it when we put it in the equation, right? That's what you were saying?
Yeah.
Okay, yes. So once it's squared, it just becomes this. So that's your distance there. And those are your two x things, your two x fields. You have an x field from here and you have an x field from this one. Your y field is going to look just like this, right? Your y component is going to look just like this. Let's see, what am I doing wrong here? I'm doing something wrong. No, I'm not. I'm doing it right. Your y one is going to look just like this because it's also at x and y distance. And then you're going to have another one in the y direction from this one at a distance of y, right? Once you're done with these, then you have to figure out which direction each one of these go. And it's going to have to, it has to do with the sign, right? So the sign of an electric field from a negative one, or the direction of an electric field, is towards the charge. So this one is, the arrows are actually wrong. I actually put the arrows in wrong, so let's erase those really quick. Because the arrows should always go towards a negative charge, so let's redraw them. The arrows for an electric field should always go towards a negative charge, so they should look like this for this charge. But for this one, they go away from a positive charge, so it looks like this. This one, it goes away from a positive charge, so it looks like this. So these ones have electric field. This one has an electric field that is pointing down, which in our component system, in our coordinate system would be negative. This one has an electric field that's pointing left.
Shouldn't you just do the math first, and after you're done with the math, put a sign on it?
And that's what I did. I did the math first.
You just have to erase
I'm just not putting any
I
numbers
worry
in.
about numbers because
Yeah, that's what I did. This is the math. Now I'm looking at direction.
Because y looks the same, E3 equals K, Q1 divided by Y.
Yeah, it'll be, that's right. For the y, there will be an E1, which equals KQ1 divided by y squared.
Do you Q2 the same way?
Yeah, it'll be E2y will equal KQ2 times x squared plus y squared, or divided by x squared plus y squared, right? So it'll look very similar over here, but for this charge and this component. And then we got to assign signs to each of these, by which direction the field is going, right? In this case, the field is going away from this positive charge, so it's going down, so it's actually negative. The field is going away from this charge, so it's going left with that, which is actually negative. So the electric field from 3 is actually negative. And the electric field is going upward and to the right for Q2. So even though Q2 is the negative charge, it actually creates a positive field at this point. So those become positive for E2x and E2y. And that's what makes this challenging. Nothing else is really new. We have some very simple equations to calculate vectors for force and electric field. But figuring out the directions of the field is the challenge.
Here's my question then. If if you rotate that and you make one of them a 0,
Put one of these at 0,
yeah.
it changes everything.
Yeah, if you put one of them to 0, then you just have to figure out the other two,
Yep.
and then whether they're positive or negative, and that's what's happening at your one that you're considering fake.
That's right. So we don't necessarily have any kind of base in this problem. We've just chosen the point at 0, 0 to be the place where we want to calculate the electric field. And this is the big difference between having field physics and other kinds of physics. We can just go out there in space somewhere and say, I want to know the electric field at this point. There doesn't have to be anything there. We just want to know the electric field at that point, and we start to calculate it. But we do have to look at each charge separately and say, what is this thing doing? It has a field going towards it. It has a field going away from it. It's pulling on a charge. It's pushing on a charge. There's a lot of things to sort out.
Yeah, but you don't really care what the charge is. You do each section separately and then put
That's right. If you do each one separately and then put the directions on afterwards, you can keep track of it fairly easily. But you do have to stay organized and make sure that you keep things, kind of figured out.
you got you just turn it into a one-dimension problem and just work.
That's right. Much easier to do two one-dimension problems in X and Y than it is to try to do it all together. And then put it together at the end, right? All right. I still think I did something wrong here, but I don't. What did I do wrong? Did I do something wrong?
Is it the components of the second one?
You got into that.
The components of Q2, the distance is, you're using the hypothesis.
Charge.
Shouldn't they have different charges? Because they're from different distances?
No.
Not different charges, different field strengths, because they're from. No?
No.
Because you're going to the same point, your field strength is the same. But I don't understand those why it isn't half. Because you're taking one and the other, it should be negative. Subtract one from the other or something. Something don't look right there because you're
I think it's right, but I'll check it. I have to skip it.
because you're taking two of the same thing and adding them together where that's not right.
Right.
It should be like, yeah. Because if you take your hypotenuse, it's one subtract.
The Q2 looks too big.
It is. It is. That's not right. Because you can't use that for both. Because one should be 1 minus x squared, the other one should be 1 minus y squared. But then a minus a equals, a plus a squared plus b squared equals c squared. Alright, so we're going to change it around. Yeah. So that's not right.
It's just gone.
Huh?
I think it's-
What is induction? I know what it is, but I don't understand the induction. Charging, induction is charging our contact. Separation charge.
Inductions would be charged by ground or other non-contact means. I believe they have charged by ground. We charge by ground here. Well, I will see you Tuesday, correct? All right.
Open your thing, I wanna see if it's
Open what? Oh. Hold on, please, let me end this video really quick.